In my previous class, I told you about the IR spectrum of alkene, and alkynes. Today, we will discuss about the IR spectrum of aromatic compounds and other functional groups as well. So, first of all, I will discuss about the IR spectrum of the aromatic compound. In case of aromatic compounds, we have different type of vibrations. And what are these vibrations? It may include generally 5 regions. And what are these 5 regions? Number 1, this is the carbon hydrogen stretching vibration, and this particular carbon hydrogen stretching vibration will appear above 3000 centimeter inverse. The second one is the vibrations between 2000 centimeter inverse to 1700 centimeter inverse, and this is particularly a region in which different type of overtones will appear. Next one is the skeletal vibration, and these skeletal vibrations, there are generally 4 peaks, and these 4 peaks will appear in this particular region, means the region between 16502 to 1430 centimeter inverse. So basically this is a region which will tell you about the skeletal vibrations in case of aromatic compound. Means if we are having 4 peaks at this particular region, at that time we can identify easily that this compound is aromatic in its nature. Otherwise aromaticity is not present in the particular compound. And the next one is, because of the carbon hydrogen bonding vibrations, and it will include again the 2 type of the vibration. This is in plane bending vibration, which will appear at around above 1000 centimeter inverse and 1000 to 1275 centimeter inverse, and the out of plane carbon hydrogen bonding vibration, it will appear between 900 to 690 centimeter inverse. So these are the different type of peaks a aromatic compound may have. Now we will have different type of, either the aromatic compound is monosubstituted, it will be orthosubstituted, it will be meta, or it may contain the para substituent present at its position. So how it can be identified? On the basis of this one, I can tell you that if the aromatic compound is monosubstituted, at that time you will have 2 additional bands, and these 2 bands will appear either at 690 to 710 centimeter inverse, and the second one will appear at 730 to 770 centimeter inverse. Similarly, if the aromatic compound is orthodisubstituted, at that time you will have only a single band, and that single band will appear between 735 centimeter inverse to 770 centimeter inverse. Similarly, for the meta-disubstituted benzene ring, if I am particularly talking about, again you will have 2 different type of the bands, and these 2 different bands will appear at between 690 to 710 and between 750 to 810 centimeter inverse. And if I am particularly concerned about this para disubstituted, at that time again you will have a single band, and that single band will appear between 810 centimeter inverse to 840. Now generally in case of carbon-carbon double bond, that is, again the skeletal vibration will appear between this one. Now there are some IR spectrum of different aromatic compounds, and I will analyze these spectrum in front of you. For example, this is the peak, and what is this peak? This peak is, because of, I am talking about, this is the main peak of this aromatic compound, and this is the carbon hydrogen stretching vibration, and this is because of the unsaturated carbon is here, and that unsaturated carbon is attached with the hydrogen. So this is your unsaturated carbon hydrogen stretching vibration, and is appearing above 3000 centimeter inverse. So this is your the spectrum of this particular ethylbenzene, in which this is a monosubstituted benzene. Now the second one is, this is the benzene ring. Now this peak is for benzene ring, and this is between 1500 to 1600 centimeter inverse. And how it can be characterized? It can be characterized by these four peaks. One, this is your second peak, and this is your third peak, and this one is your fourth peak. So these four peaks correspond to the compound, that the compound is particularly aromatic in its nature. So this is your benzene ring peak. Now we come to the point that this particular benzene is monosubstituted, means only one substituent is attached at this particular position. So at monosubstitution we are also obtaining two peaks, and these two peaks are appearing at 690 to 710 and 730 to 770 centimeter inverse. So all the information is being conveyed to this particular compound. Now we come to the second example, and this second example is ortho-xylene, in which this was particular toluene. When the CS3 group is not attached with the compound, this is particularly toluene, and when one CS3 is also attached at the ortho position, this was get converted into the ortho-xylene. So in case of ortho-xylene, what is happening here? Again, we are having, this is unsaturated carbon and hydrogen stretching vibration, which is appearing at above 3000 centimeter inverse. So this is that particular peak. These peaks, in which one of the peak is now deformed, sometime this kind of IR spectrum may also be obtained. So these peaks are because of this aromatic ring. So this is that peak which tell us that this particular IR spectrum belong to the benzene ring. And this when that was monosubstituted, at that time we were getting two peaks. Now this is single substitution, and that single substitution is at ortho position, where we get only one band, and that band is appearing between 735 to 770 centimeter inverse. So this is that peak, and it will tell you about the ortho-xylene. Now we are getting the para-xylene. At this time, para position is here. Again, this is your unsaturated carbon hydrogen stretching vibration. These peaks, this is a very simplified spectrum. When the spectrum gets simplified, generally the small peaks are being diminished, and this is the reason that we are not getting that particular peak very with good intensity. But again, this is the peak which is because of the aromatic ring. And this is the para position, in which we only getting a single peak, and that peak will appear between 810 to 840 centimeter inverse. So this is a single peak will be appeared, and this will tell you about that it is para substituted. So this is your para-xylene. Now come to this one. This is your meta-xylene is here, and in case of meta-xylene, at meta position we will get two different type of the peaks, and these are the two peaks which we are particularly obtaining at this position, and this is between 690 to 710 and between 750 to 810 centimeter inverse, and we are getting this particular peaks. And this is again unsaturated carbon hydrogen stretching vibration, and these peaks are because of the aromatic ring, and this is the case of the meta-xylene. Now we come to the styrene, and in case of styrene, this is the saturated carbon hydrogen peak is not here, because there is no carbon in all those compounds. We were also having the saturated carbon hydrogen peaks. For example, if I'm particularly concerned about these peaks, for example, here we are getting the saturated peak as well along with the unsaturated peak. But in case of styrene, as all core carbon are doubly bonded, sp2 hybridized, and this is again there is no single bond, and that's why there is complete diminishing of this particular peak, which is the saturated carbon hydrogen stretching, and that is completely absent in this case. And there is again a stretching vibration of carbon-carbon multiple bond, and it appears at 1640 centimeter inverse. That will tell you that outside the ring there is also a double bond, and this is because of the aromatic ring, that is the benzene ring. And now this particular peak between this 910 to 920 and 990 to 1000, that is because of this particular RCH double bond CH2, means when one of the hydrogen is replaced in case of alkene with a substituent. So this is the benzene and this will act as a substituent here, and this is hydrogen which is replaced with this particular benzene, and this peak appear because of this reason. So this will tell you that outside the benzene ring there is a carbon-carbon double bond. So this is the particular IR spectrum of styrene. Now this is again a case of the monosubstitution, in which we are getting a particular this particular peak in which it is telling you about the monosubstitution, and this is the two peaks which are appearing here. Now we are particularly come to the second second of the IR spectrum, and that IR spectrum is case of 2-phenylpropene, and this is the structure of 2-phenylpropene, in which we are having this carbon-carbon double bond, and to one of the carbon 2 hydrogens are attached, and to one of the carbon the 2 hydrogens are replaced with CH3 group and the phenyl ring. So we are having this type of alkene in which disubstitution is here, R2C double bond CH2, and for that particular disubstituted alkene we are getting a particular peak at this region. Again we are getting two peaks for the monosubstituted benzene ring. We are getting these peaks for the aromatic system. We are getting a saturated carbon hydrogen peak as well, that differentiate this particular IR spectrum with the previous IR spectrum of styrene molecule, right? And this is again the unsaturated carbon hydrogen stretching vibration, and this is because of the presence of the benzene ring. So this is benzene ring. Again there is a saturated carbon hydrogen stretching vibration, unsaturated carbon hydrogen stretching vibration, and this is the vibration because of the disubstituted alkene, and this is tell you about that the benzene ring is monosubstituted, and two peaks will appear here. So this is the spectrum of 2-phenylpropene. Now we come to para-methylstyrene. In case of para-methylstyrene, you will have the saturated carbon hydrogen stretching vibration. You will get a phenomena, in case of para substitution you are getting only a single peak, and this is a single peak, very prominent and very sharp peak will appear here, and this will tell you that this particular molecule is para substituted. Again you will have this is the case that the molecule is RCH double bond CH2. So again you are getting these two peaks because of the RCH double bond CH2. Again you are getting a peak because of the C double bond C. You are getting the peaks because of the aromatic ring. You are getting the peak because of the saturated carbon hydrogen stretching, and you are getting these peaks because of the unsaturated carbon hydrogen stretching vibration. So from this IR spectrum we can easily identify that what are the characteristics peaks for the aromatic system that will help the chemist to elucidate the structure of the aromatic compound, and these peaks will include the carbon hydrogen stretching vibration, the carbon-carbon double bond stretching vibration. There are 4 peaks will appear: carbon hydrogen out of plane bending vibration and carbon hydrogen in plane bending vibration. On the basis of that we can easily elucidate the structure of the organic compounds. Now we discussed the spectrum of the alkynes in our last class. Today we will also discuss the spectrum of the nitriles, that is the cyanide or C triple bond, and there is also a triple bond in case of this nitriles between particular carbon and nitrogen. So this is the spectrum of butyronitrile, in which what we are getting here, this is carbon triple bond nitrogen stretching vibration, and there is a very sharp peak for this particular C triple bond nitrogen, and this will appear at 2249 centimeter inverse. So basically this is an indication, and this because of this particular C and triple bond, this band has a very sharp and pointed shape. This is your sharp and the pointed shape is here, and this is just like the alkyne carbon triple bond carbon. But because the C and triple bond is more polar, as we know that this is particularly more polar as comparison to carbon triple bond carbon, this band is stronger than in case of alkyne. Means in case of alkyne, if we want to particularly differentiate on the basis of the IR spectrum between alkyne and nitrile, at that time we will have to identify the strongness, we will have to identify the sharpness of this particular CN band, because CN triple bond is very polar, and because of this band is very stronger than in case of alkyne. So this is the information we can obtain from the IR spectrum of the nitrile compound. So now we will come to our second is alcohol and phenols. So this alcohol and phenol, in case of alcohol and phenols, one thing you will have to be very clear in your mind is presence of intermolecular, and in case of phenyl maybe intramolecular hydrogen bonding. So what kind of different vibrations can be happen in case of alcohol and phenols? That will include the OH stretching vibration, and because of the CO stretching vibration is here. Now I am telling you about the OH stretching vibration. If we are particularly concerned about this stretching vibration, it will be affected by the hydrogen bonding. First of all, you may have a free hydroxyl group, and that free hydroxyl group will absorb between this particular region, that is 3650 to 3585 centimeter inverse. And what will be the characteristic peak? It will be very sharp and it will be very strong. So a sharp and a strong peak at this particular region is because of the free hydroxyl group. Now, how this free hydroxyl group can be generated? Either into the vapor phase, if the particular IR spectrum is obtained in case of vapor phase, at that time the hydroxyl group will be free, or that will be in very dilute solution of any non-polar solvent. For example, we may have carbon tetrachloride as our solvent, and in that solvent this free hydroxyl group can be generated, and we will have a very strong and sharp peak at this particular region. You may have intermolecular hydrogen bonding, and that particular intermolecular hydrogen bonding will increases as the concentration of the solution increases, or when the sample is analyzed neat. Means if we are increasing the concentration of that particular solution, the chances of intermolecular hydrogen bonding will be increases, and because of intermolecular hydrogen bonding, the hydroxyl group will now not be free, and when it will not be free, it will not give you a sharp peak at this particular region. Now the peak will be because of the hydrogen bonded hydroxyl group, and that will lower the frequency of the absorption, and now it will appear at 3550 to 3200 centimeter inverse. So this is the effect in case of alcohols, and in case of phenols, how the OH stretching vibration will appear at lower frequency as compared to its actual frequency in that case. What is the reason behind that? The reason again is, I have already told you in the previous slide, the reason because of the hydrogen bonding, and because of the hydrogen bonding the force constant will be lower, and because of when the force constant will be lower, the vibrational frequency becomes lower, right? So that is only because of the hydrogen bonding, in which the force constant will become lesser in its value, and when force constant will be decreased, at that time your vibrational frequency go on decreasing. This is the case of IR spectrum of the 1-butanol, and what information can be conveyed by this IR spectrum is, this is the sharp peak I was talking about. You have analyzed the IR spectrum of different kind of compounds, alkane, alkene, alkynes and aromatic system. You have not seen this type of sharp and a prominent peak, but this peak can only be observed in case of alcohol. So this peak is particularly because of the hydroxyl group, and this is the peak I was talking about, for example this one. And how we can say that this is free hydroxyl group or this is intermolecular hydrogen bonded hydroxyl group? That can be analyzed on the basis of the frequency of this particular peak. Now we can also have a carbon-carbon stretching vibration is also here. Carbon-hydrogen stretching vibration will be here. So this is the vibration that is carbon-hydrogen, that is saturated carbon-hydrogen stretching vibration is also here. And finally, what information other than this can be conveyed by the IR spectrum is that this is, either you may have primary alcoholic group, you may have secondary alcoholic group, or you may have tertiary alcoholic group. So in that case, the peak will be different whether you are having primary, you are having secondary, and you are having tertiary. For example, this is the case of primary alcoholic group. So here a peak will appear at this one, and on the basis of this peak we can identify that the alcohol is primary alcohol and this is not secondary and tertiary. For example, this is your tert-butyl alcohol. In case of tert-butyl alcohol, because this hydroxyl group is attached with the carbon, this is tertiary in its nature. So here we are getting a prominent peak, and this peak identify that this particular IR spectrum belong to tertiary alcohol along with this particular hydroxyl group. This is a sharp peak of hydroxyl group, and this is the peak for saturated carbon hydrogen stretching vibration. So this is the case of tertiary butyl alcohol. Now we may have methyl and propyl ether. I will tell you the difference. For example, this is the tertiary butyl alcohol, and this is the case of ether. In case of ether, what will happen? There is a carbon-carbon connectivity, so carbon-carbon vibration will be here, carbon-hydrogen stretching vibration will be here, and there is oxygen and carbon, means there is carbon-oxygen connectivities here, so there will be a vibration of carbon and hydrogen. Now what will happen, that there will be no hydroxyl group peak at all, and this particular absence of this particular peak is saying you that this particular spectrum is not belonging to the hydroxyl group. Either the presence of this particular carbon oxygen stretching vibration here, which absorbed at around 1300 to 1100 centimeter inverse, is because of the ether, and this is not because of any alcoholic group. And absence of this particular peak is also here, so we can confirm it that this particular group, this particular IR spectrum belong to ether category. This is again a IR spectrum, and this IR spectrum is because of the hydroxyl group is here. This is your saturated carbon hydrogen stretching vibration. I was telling you about this one, and this is CO stretching vibration is again here, which you will tell that this is a case of 1-butanol. So this is a case of primary alcoholic group. So this is ether, and this is your alcohol. Again, this is your ether, and this is your alcohol, and this is your another alcohol. That will tell you about different type of groups that coming at this position. Particularly if we are concerned about this one, that this is your primary, this is your secondary group is here, and similarly you may also have a secondary group, and that particular secondary group will have a peak at around 1100 centimeter inverse. In case of primary, the peak will be at 1050 centimeter inverse, and in case of tertiary, it appears at 1150 centimeter inverse. So we can identify between primary, secondary, and tertiary alcohol on the basis of the IR spectrum. Tomorrow we will discuss about the IR spectrum of the phenol and some more functional groups regarding this one.